In this video, we're going to look at uses of electromagnets. So an electromagnet is a type of induced magnet. It's a temporary magnet that is made when electricity passes through a wire. So whenever we have a wire with a current flowing through it, there will be a magnetic field around that wire. Okay, and I'll make another video that will go through this in detail. So here we have an electromagnet. It's not a very good one, but we have an electromagnet. We have electricity passing through the wire and we get a B field or a magnetic field. So how do we make a stronger electromagnet? So we can, of course, have many lengths of wire in a short space. That's basically just saying we can make a coil. So the typical electromagnet that you will see is a coil of wire. Right, so this is obviously a much better electromagnet. Coil of wire. Now this has a special name. This is called a solenoid, which students do need to know. That's just a fancy word for a coil of wire. So how can we make it stronger? We can have more coils in the same space. We can increase the current. That is important. You should get students to get into the habit of saying increase the current, not increase the voltage. If you increase the voltage or the potential difference, you will increase the current as well, assuming the resistance stays constant. But it's the current that it results in the magnetic field, not the voltage. So we should say current. And the third thing we can do is to add an iron core. So we can get our solenoid and we can actually, inside it, we can put a piece of iron that fits inside it. And because iron itself can be ferromagnetic, or it can certainly be very easily induced to turn into a magnet, this amplifies the strength of the field. As all the little domains inside the iron all line up, they add together, they reinforce, because of course the magnetic field is a vector, and they amplify that magnetic field. So these are the three things that we need to know about to increase the strength of the field. What does the magnetic field around a solenoid look like? It basically just looks like a bar magnet. So I'll draw it here. So just like a bar magnet, we're going to have some field lines that basically go off to infinity, some field lines that go around in a circle, and then usually one that goes straight through the middle. So what's important here is that they're relatively evenly spaced. So this isn't a great diagram here because these are not evenly spaced. It's a little bit better on this side. Obviously none of them touch, and we don't want too many, so 5 is entirely reasonable. How do you know which direction the arrows should go, and how do you know whether it's a north or a south pole? So what you need to do here, you need to get your right hand, and it has to be your right hand, and you need to make kind of this shape here, right? So you're almost making a solenoid with your fingers. And then what you actually have to do with your fingers on your right hand is you have to say, right, if the current is going along my fingers in this direction here, then the north pole is where my thumb is pointing. So this is my north pole. And then obviously the south pole is this end. So if we take our solenoid here, it's going round and round. This isn't obviously the clearest diagram in the world, but let's say that the current is going this way and this way, this way and this way, this way and this way. Then when I put my fingers over it, my finger's going to line up with these points here, goes over, and the north pole will be over here, and the South Pole will be over here. Okay, so it's the right hand rule, right, where our fingers are the wires. What are some uses of electromagnets? There's 3 common ones that come up, but I'm going to go just over 2 of them here. So one of them is a circuit breaker. So students know what these are because everyone has them in their house, and some classrooms even have them in. This is a resettable fuse. Now, students don't actually need to know the details of these. Older exam syllabuses had these in a bit more detail, but they might ask the basic function of these. So what we have here, we have our live wire coming into the house. It goes through a coil of wire with an iron core in. So it's going through an electromagnet, goes through the wire, through these contacts, and then through here to the house. And at the bottom here, we have a spring, which is the reset button. So in normal operation, this works just as a closed circuit. The current goes through, we've got a complete circuit, and then we can make our circuit work. If the current gets too high, what happens, this then becomes an electromagnet with enough strength to attract this contact to it. As soon as this contact goes to here, the circuit breaks here. So now we haven't got a complete circuit anymore, and of course the current will cut out, right? And now our house is protected from an overload. This bar here is attached to a longer arm that will pop out a button here, and then you can of course press the button back in, and that will reset it. So that's exactly what happens to in your house. If you create a short circuit, if you spill water on your plugs, for example, the button pops out, you have to go to it, flip it down, and then it pushes this back into contact. Now we have a complete circuit again. The second common example, and we do also have a demonstration version of this, which is really nice, is an electric bell. So here we have our circuit, we've got our solenoid with an iron core. Iron core, of course, makes it stronger. And then the circuit will go this way, and it will be a complete circuit. When the circuit is turned on, usually there'll be a switch here as well. When the circuit is turned on, the current flows through here. We get a force of attraction from the iron bar to the solenoid. This means that the metal, or whatever this is, metal hammer will strike the bell, but this whole thing is connected. So when it strikes the bell, it breaks the contact here. So this now turns off the circuit, turns off the electromagnet. As soon as the current stops, the electromagnet turns off. And then it will ping back into place. Okay, so there will be a spring somewhere, which I haven't drawn on. There'll be a spring here, for example, that will pull this back, and then it will make the contact again, and then the electromagnet will turn on. The electromagnet will attract this arm, it will hit the bell, it will break the circuit, and the spring will put it back, and so on and so on. The demo of this is really nice because you can just repeat the process, 5-10 times, and students then very quickly know what's going on. The third common use is a relay switch. It's very, very simple. It's quite similar to this, except that when you turn on the electromagnet, it doesn't break a circuit, it actually closes 2 contacts together. And the advantage of a relay circuit is that you can use a very small current to turn on a big current. So your car will have something very similar, or other devices where you possibly turn it on by hand, but you don't want to be actually closing the switch in a very large current circuit. You need some degree of protection from that. They're really, really simple diagrams. but I'm not going to go into it now. The last thing that I want to say, which is hopefully fairly obvious, is that if we want an electromagnet to work in a circuit, we need DC currents. That means direct current, where the current flows in only one direction. If we had alternating current, this wouldn't work because the current would be going back and forth constantly in direction, and so the magnetic field will be changing direction really, really quickly. And of course, that's not going to be of any use to a magnet. We need a DC current so that the field is constantly in one direction.